Next, we have talk by Cannon Conjecture, and maybe I just want to quickly remind that right after his talk, there's no break. We have problem session, and I guess Michelle's problem session is going to be in the other room, run by Tommy, and problem session for Daniel's reading course is going to be here with Lorenzo.
All right, thanks very much. Admission on Tuesday, when I defined PDN groups, you should assume that the group has property FP. It's not a consequence, you should assume it. So you need to assume that you have a finite resolution of Z by finitely generated projective Z gamma modules. Okay, that should be an assumption and it's not a conclusion. So I apologize for that. But I'm not going to do any more homological algebra today, so I won't write anything about that. You should just go back and adjust your notes if you have them. So for the next, remember, if you recall what we finished with on Tuesday was this statement that a PD3 group admits a possibly trivial graph of groups decomposition where the edge groups are Z squareds and the vertex groups are either fundamental groups of Seifert fibered three manifolds or are atoroidal in the sense that every Z squared subgroup is contained in the conjugate into the edge groups. And so that led us to two separate questions, one of which was atoroidal implies hyperbolic or relatively hyperbolic. So if there are no Z squared subgroups at all, are you a hyperbolic group? And if all of your Z squared subgroups are conjugate into this peripheral structure coming from the edge groups, are you relatively hyperbolic? And we'll talk some more about relatively hyperbolic groups tomorrow. So that was the first question, atoroidal implies hyperbolic. And the second question was, once you have this Gromov hyperbolic or relatively hyperbolic structure, that's some sort of coarse negative curvature, can you upgrade that to a nice action on H3? And so that you're really the fundamental group of a hyperbolic three manifold, or even can you find a three manifold? Once you find that three manifold, then known things from geometrization and so on will tell you that that three manifold has to be the appropriate kind of hyperbolic three manifold. So there's two aspects. Atoroidal implies hyperbolic, and this implies coarse hyperbolic, and then does coarse hyperbolic imply real hyperbolic? And I'm going to focus on the second ones, which we talked about as the Cannon conjecture in the case the graph of groups decomposition was trivial. So that's what I'm going to focus on. There are lots of approaches to the Cannon conjecture, and I'm not going to talk about most of them. Maybe the one that I think is one of the most beautiful, and this is homework, because I'm not going to talk about it. You should read Cannon's paper. It's called the combinatorial Riemann mapping theorem, because it's just a beautiful paper. And if you haven't read it, you will learn a lot reading it. Maybe I should set that as an exercise. We could all just sit in this room and read that paper in the next hour. It's a really amazing paper, and if you've read it, you'll learn more reading it again. So that's that was an approach to proving the Cannon conjecture by Cannon, and then Cannon, Floyd, and Parry, and Cannon and Swenson and so on had some ways of thinking about that. But really, they are saying, okay, well, if our Cannon candidate, a hyperbolic group with two-sphere boundary, were to be a hyperbolic three manifold group, then the action on the boundary would be by Mobius transformations. If we could find the right metric on the boundary to see that. So you'd need a conjugation of the boundary that you see to the round sphere so that the action conjugates to an action by Mobius transformation. So you're upgrading this dynamical action on the boundary to an action by conformal maps of the round sphere, and that was the approach that they were taking. And Cannon in this paper comes up with a criterion for a metric on the sphere to be in the same quasi-conformal class as the round metric. That's an amazing paper. But that's all I'm going to say about that. I want to focus, and there are other approaches that involve other parts of the boundary, work of Bonk and Kleiner on L4's regular dimension of the boundary and other such things. And I'm also not going to talk about those. I'm going to instead, well, here's a theorem, and we'll focus on things around this theorem. And this theorem is due to Markovich. And in the formulation I'm going to give, it's due to Heisinski. but it's basically Markovitch. So gamma, a hyperbolic group with the boundary of gamma S2. If gamma is virtually compact special, then gamma is virtually I1 of closed hyperbolic three manifold. Okay, so this is in paper by Markovitch called a criteria for the Cannon conjecture and Hazinski. So Markovitch did something that's basically this, but not quite exactly this theorem. And this theorem exactly is found in Hazinski. Okay, so that's this gives you an approach to proving this Cannon conjecture. Namely, your goal is to prove that such things are virtually compact special. Okay, so what's my plan? I'm going to start today. I should say Hazinski has some more general statements than this about things where the boundary is a proper subset of the sphere and not just the whole sphere, and has some non-conditional results as well as things about the case where the boundary is a Sierpinski carpet, for example, and other things. Okay, so my plan for today is to give you like a 6.5-minute crash course in the proof of the virtually special theorems in the hyperbolic setting. You can time me and I'll stop after 6.5 minutes. And then I should have taken 6.5 minutes from Michelle. That's right. Yeah. And then after I do that, I'm going to prove what looks like a total. Like I'm not going to prove this theorem. I'm going to show you something else instead. But hopefully you'll see that it's related. So cubes is the first thing we want to do. So Michelle's told us a lot of the consequences of being virtually compact special, and I want to use those, and I'm going to need one more consequence of it that is sort of I'll explain why it's not something that needs stating in the three-manifold setting, but in a more general setting, it might be very important. But what we haven't talked about at all is how you go about finding these actions on cat-zero cube complexes. Which is another way of thinking about virtually compact special. So Michelle defined it in terms of these nice embeddings into right-angled Artin or Coxeter groups. There's a different way of defining it in terms of nice actions on cat-zero cube complexes. And then Hagelin and Wise defined both of these and showed that they're equivalent and so on. And so how does one find such nice embeddings, or on the face of it, how does one find actions on cube complexes? And that's really the Segev construction and various upgradings of that due to many people. So let me just briefly tell you what happens with the Segev construction. So here's a definition. So we have G, a finitely generated group, and maybe with Cayley graph still, as usual, it doesn't matter which Cayley graph you take or which other space you take that you act geometrically on. And now we have some subgroup H of G, and this is what's called codimension 1. If when I take the Cayley graph of G and I factor out the action of H, so this is something that's known as a Schreier-Coset graph. But you just take the Cayley graph and factor out by the H action to get, well, if this was simply connected by adding two cells, this would be the cover whose fundamental group is H of the presentation 2 complex. Okay, so if this has more than one end as a topological space. Okay, so there's inside of here, you should think, well, there's a special thing that is, so the vertices of this are now cosets of the form HG, and there's a favorite one of those, namely H. So H is sort of sitting here in a compact part of this space at a single vertex. You should take a neighborhood of that in this Schreier-Coset graph, and then that separates into more than one deep component, and then maybe larger neighborhoods separate into more components or not. So for an example to keep in mind, groups of spaces, so you should take G to be the fundamental group of a surface. And then inside of that surface, you should take H to be the thing that's generated by a curve. Okay, so the universal, so the Cayley graph of this is the hyperbolic plane, basically. And now you take the hyperbolic plane and you factor out by the cyclic subgroup generated by this simple closed curve, or you take the cover of this surface to which this curve lifts and whose fundamental group it is. And so H2 mod H in this setting is an annulus, where this curve lifts and everything else unwraps to be a giant flaring annulus. And so there are two ends. Okay, so this codimension one submanifold of this surface represents a codimension one subgroup. It's not quite that simple, but this is sort of where some intuition comes from. All right. So now Sagiv says, given this, you can build a cube complex. So given a G and an H, or even a finite collection of H's, you can build an action of G on some cat-zero cube complex. Do you have a question? Yeah, nearly, not quite. So you might have a non-orientable surface and a one-sided curve. And then, I mean, the lift of that is like, yeah, so yeah, so you need it also to be pi1 injective, so that you sort of the group theory is being faithfully. So if you took a one-sided curve in a surface, which of course is codimension one, then this cover is actually an infinite flaring Mobius strip instead of infinite flaring annulus, and it has one end. So this is not quite a perfect analogy. In fact, it's a long way from a perfect analogy, but it's a pretty good analogy nonetheless. Okay, so this is what Sagiv does, the Sagiv construction. So we take G and H in G codimension one, and then we build this thing called a cat-zero cube complex X with a nice G action. Okay, and I wanted to spend, I don't know, I've got like -3 minutes of my 6.5 minutes left, so I wanted to spend -2 of them talking about this construction. So the idea is you look at the universal cover, you look at G, and you have some H's in there and some translates of H's in there, and they look sort of like this. If I was lifting a non-simple closed curve, I get some picture that has some of that kind of aspect to it. And you should orient, so orient the complements of G minus some neighborhood of G. So I'm thinking that like H really separates into two components, and so do all of its cosets. So you should orient all of these. You just choose an orientation. You just say H points in that direction, and this one points in this direction, and this one points in this direction. And then there are some consistency requirements. I'm not allowed having, so this guy has two half spaces. One of those completely contains this half space that I've already chosen. I'm not allowed to choose the one pointing away. I now have to choose this one here, and I have to choose this one here. Okay, and I look like I'm pointing at a region in space, but I'm not quite doing that. Okay, so then there's a consistency criteria. The vertices of the cube complex are allowable orientations. The edges in the cube complex are allowable orientations that differ on exactly one coset. And then you fill in cubes when there are cubes. There's going to be a little cube here, probably, because I can choose, on these two things, I can choose any one of the 4 possible orientations independently. But these two things here, I can't choose any one of 4 independently. There's only 3 that I'm allowed to choose. So they're not going to give an edge, a square. They're just going to give a pair of edges. All right, so, all right. This is not a definition. This is an idea of the construction, and it works in settings that are related to, but not exactly like this. Things like wall spaces that you might hear of, and other such things. So Sagiv made this construction, and then he proved a theorem as well. He proved many theorems, but here's a theorem that's particularly important, I think, for this construction. So G hyperbolic, and you can do this not just for one but for a family of codimension 1 subgroups, and suppose they're quasi-convex, like they are, for example, in this picture here. So then the action of G on the cube complex is co-compact, no matter what you do, as long as you choose finitely many. So in this case, when it's just a simple closed curve on a surface, the cube complex that you build is going to be the Basset tree of the splitting that comes from cutting along this and applying Van Kampen's theorem. That's a one-dimensional cube complex, and you act on it co-compactly with quotient and edge. Okay. So you always get co-compact action. In this example, you don't get a proper action. This is an amalgam, and the edge groups are free groups of rank 2. So it's definitely not a proper action. There are massive stabilizers. Okay, so co-compactness in this setting, and in other settings, it's hard to get co-compactness. In this setting, co-compactness comes to you almost for free. Finding codimension 1 subgroups might be hard, making them quasi-convex might be even harder, but if you can do that, then you automatically get a co-compact action. Getting a proper action is harder, because getting a proper action, I'm going to have to cut this surface up entirely so that there are no big chunks left over. So you have to find lots and lots and lots of them. Okay, and there are various ways of formalizing that, and most of the ones that I know about are due to Johnny and collaborators, and the one that I wanted to focus on today is due to Bergeron and Wise, because it sort of sees things from the boundary. Nope, that's a theorem. It's also a theorem that it's non-positively curved, and that, yeah. So that's all done by Segui. Yeah, so here's a theorem, Bergeron and Wise. They say the following. So suppose G is hyperbolic. And now suppose that for all pairs of points, maybe distinct pairs of points in the boundary of G, there exists a quasi-convex codimension 1 subgroup H that depends on the points A and B, so that okay, so now in the boundary, we have our boundary, and it's a 2-sphere boundary, because that's what I can draw, and that's what we care about this week. Codimension 1 subgroup, you should think of it like a surface subgroup, because that's 1 less than 2 is like 1 less than 3. Quasi-convex means the limit set is a circle, so there it is, and it separates into 2 components. In general, it might be more components, because it could be a more complicated thing than a surface, but okay, so what's the condition? So what you want to be able to do is, given A and B, find a surface, quasi-convex surface that cuts A and B, whose limit set separates A and B. So such that A and B lie in different H orbits of components of the boundary of gamma minus the limit set of this subgroup. So the limit set that was introduced at some point by Michelle this morning, not just at some point. Okay, so there are really lots and lots and lots and lots of quasi-convex codimension 1 subgroups, because this is obviously, there's infinitely many a priori. So Bergeron and Wise have a nice compactness argument that says then there exists a finite subcollection of the whole family of all of these infinitely many possible ones, such that the action on the associated cube complex from this construction is geometric, so proper and co-compact. Maybe I'll just say that. So it's not just co-compact. Segui gave us that to us automatically once we took the finite subcollection and co-compact. Oh, sorry, gamma is hyperbolic. Yeah, sorry, gamma is hyperbolic. Yeah, sorry, gamma is hyperbolic. Thanks. This is a capital lambda, and it's for the limit set. So a quasi-convex subgroup of a hyperbolic group is itself hyperbolic, and that embedding induces an embedding of the boundary of H into the boundary of gamma, and that image of that embedding is called the limit set. And so it's just the ordinary limit set. Not necessarily. I mean, in my picture, it is. It could actually, you could take something whose limit set was a Sierpinski carpet, and that would separate the sphere into many, many components. And no, but you're interested in H orbits of components. Yeah, it doesn't have to be a sphere. That's right. It's for general boundaries. I drew a sphere, but it's for general boundaries. Yeah. Okay. How am I doing? Terribly. Great. All right. All right. So what's next? So why this is a great criterion and it's very useful in lots of situations. In the setting of three manifolds, Kahn and Markovitch solved what was called the surface subgroup conjecture. If gamma is pi1 of closed hyperbolic M3, then gamma has a quasi-convex surface subgroup. In fact, it has so many that you can apply the Bergeron-Wise criteria. Has enough quasi-convex codimension 1 subgroups to apply Bergeron-Wise. And a consequence of this is that these fundamental groups of, admit actions on cube complexes. And then Agel proved that if gamma is hyperbolic and acts properly and co-compactly on a cat zero cube complex, then this action is nice enough that whatever it means, gamma is virtually compact special. But this action is nice enough that after passing to a finite index subgroup of gamma, the quotient cube complex is a special cube complex in the sense of Hagelin and Wise admits, and therefore the fundamental group admits this nice quasi-convex embedding into a right-angled Artin group. And then all of these consequences that Michelle was talking about that follow from Hagelin and Wise's special cube complex technology follow for such a group, okay? So closed hyperbolic 3 manifold has lots of quasi-convex codimension 1 surface subgroups by Kahn Markovitch. Bergeron and Wise tells you that gets you a nice proper and co-compact action on a cat zero cube complex via essentially the Segev construction. Agel tells you that that's virtually compact special in the sense of Hagelin and Wise, and then Hagelin and Wise tell you all of these unbelievably incredible consequences for such things, as Michelle was talking about. Okay, so one extra consequence being virtually compact special that basically follows from the definition in terms of cat zero cube complexes that's due to Hagelin and Wise, and it's like baked right into the definition, is that gamma virtually compact special implies gamma virtually has a quasi-convex hierarchy. And I'm not going to tell you what that means in writing, but I'm going to tell you in words. Homework number 2, go and read Dani's book, The Structure of Groups with a Quasi-Convex Hierarchy. Once again, unbelievable mathematics in there. The point of that book is to prove a converse theorem for this in the hyperbolic case and in some relatively hyperbolic cases, which is way, way, way harder. This basically follows from the definition, and it's what you want out of compact special in lots of situations. And then Dani goes backwards, which is just astonishing, which sort of goes into the background of many of these things. So it's what Agel uses to prove this theorem in the end. So what's a quasi-convex hierarchy? Well, our surface split along this simple closed curve. If I drew a non-simple curve on my surface, I can't cut along the cyclic group separated by that because the image is a graph in some sense. But maybe I pass to a cover and it's a simple curve now, and I can do that. That's one of the exercises in homework. And then I can cut that cover. So here, after passing to a subgroup, there's an action on a tree. The edge groups are quasi-convex. And that comes from cutting along a hyperplane in these cat zero cube complexes. Then these vertex groups, they also admit graph of groups decompositions that come from cutting along other hyperplanes, and their edge groups are quasi-convex, and so on and so on and so on. And eventually you're going to hit the trivial group. So that's a quasi-convex. All the way along the edge groups are quasi-convex, either in the big group or in the vertex group you're splitting, either both. So you're cutting it up. And this is an analog of a Harkin hierarchy, which we haven't really talked about, but which is what Harkin used to understand Harkin hierarchies and what Waldhausen used and what everybody uses. Why Harkin manifolds are useful. You have a nice surface, you can cut along it. It's pi1 injective, you apply Van Kampen. But then it turns out in the 3 manifold setting, you can keep cutting. As soon as you have a surface with incompressible boundary, you can keep cutting and you get more things. And even in not incompressible boundary, you keep cutting, get a bunch of balls. So this is a group theoretic version of that. And one of the wonderful things that virtually compact special groups have is such a hierarchy, which allows you to prove things by induction and other such things. So that's sort of a key part of the machine. All right. So that was exactly 6.5 minutes. Excellent. All right. So like I said, I now don't want to talk about Markovitch's criterion for the Cannon conjecture. I want to talk about something, well, I want to talk about the one dimension down version of that. So here's a theorem. And it's part of what's called the convergence group theorem. Okay. And it says the following. So gamma hyperbolic group. I mean, you might ask, okay, we're trying to understand groups with a 2-sphere boundary. What about an easier case, groups with a 1-sphere boundary? Okay. Let's assume, just to make things easier, that gamma has no finite subgroup. If it does, then you should factor out by it. So this is going to imply that when gamma acts on the boundary of gamma, it's faithful. Okay, and in general, the action of a hyperbolic group on its boundary might have a finite kernel. And you should kill that because why not? But I don't want to assume torsion free here because that makes life somehow too easy. So then gamma is pi1 of a closed orientable hyperbolic, words that Nathan tried to avoid at all costs. He said them out loud. He passed to a finite index subgroup so that it was a surface, but actually the group, it acts properly and co-compactly, but possibly not freely on H2. Oh, yeah, sorry. Might not be orientable, sorry. Yeah, I didn't pass to a finite index subgroup. Sorry, I just so used to things being orientable. Closed hyperbolic to orbifold, right. So this just says gamma acts on H2 geometrically, properly and co-compactly, but possibly not freely. So it's not a covering action, and you have some finite order fixed points, and those give orbifold points. And this is not, underlying space is a manifold, but there's some extra structure coming from fixed points and so on. Okay, so this is a very important theorem. It was, so Tukey proved many cases of it in '88, and then there were 2 independent proofs, Kassin, Jungreis, and Gabai, and those were 90, well, they were published in different years, but they were sort of done simultaneously and independently. So 92 and 94. So this was proved not using this language at all, and not in order to understand hyperbolic groups with a circle boundary. That wasn't the focus at all. The consequence of this, using work of many people, but in particular work of Scott and Mess, although this paper of Mess never got published, unfortunately, is the following theorem, which was the solution of the Seifert-Fibert space conjecture. And it says the following: if M is a, let's see if I get all of the closed orientable irreducible 3 manifold is closed orientable irreducible, and pi1 of M has an infinite cyclic normal subgroup. So we've seen these already on Monday. There was a short exact sequence that after passing to a finite index subgroup went 1 to Z to the 3 manifold to a surface to 1, and that was a Seifert-Fibert thing. This theorem says that's the only way a 3 manifold can do this. So that an M is Seifert-Fibert. This is a group theoretic way of seeing Seifert-Fibert manifolds from their fundamental group. Before this, it had been proved. So maybe I'll just mention one more thing, and then I'll talk about how to prove this theorem. So as part of proving that the JSJ decomposition existed, there was various things about T-squared subgroups giving closed embedded tori, and so on, or implying the existence of rather than giving. But there's a version of this theorem called the torus theorem due to Scott, from 1980 that can be phrased in the following way. So closed, again, orientable, irreducible, three manifold. So then this is a trichotomy in the way I'm going to phrase it. So either one, pi 1 of m is atoroidal. So here I just mean no z squared subgroup. Second thing that could happen is that pi 1 of the m is Harkin. And remember, in the 80s, Thurston showed the geometrization theorem for Harkin three manifolds. Or a third thing can happen, and that is that pi 1 of m has an infinite cyclic normal subgroup. Okay. And then this theorem that was finally proved more than a decade later says, oh, well, in that third case, you're actually a Seifert-Fibered space. And Seifert-Fibered spaces are pretty easy to geometrize. So, okay, well then status 1992 odd of geometrization. So a decade before Perelman, but after Thurston, this is the remaining case. Atoroidal implies real hyperbolic. Okay, so that's sort of historically why this theorem was a big deal in three manifold topology. Much bigger deal than it sort of seems to be in geometric group theory. This is really a really important part.
Each one implies hyperbolic or finite
Yeah, sorry. In the aspherical setting. That's right. And I totally just missed the Poincare conjecture. Yeah. Sorry. Yeah. In the aspherical, and that's what in my notes I carefully wrote aspherical. In the aspherical setting, we're left with atoroidal implies real hyperbolic. And then there's the finite pi 1 case where you're not aspherical. And of course, that's Poincare conjecture plus the spherical space form conjecture and so on. Okay. But look, finite groups are not interesting. So let's just think about the aspherical case. Thanks, Dave. Okay, so that's sort of a bit of theory of three manifolds from a non-three manifold topologist. So if any other lies have been told, please let me know. Mass's paper, by the way, is just a fantastic paper. He starts with this assumption, and then he finds this quotient by z. Either there's two cases. Either it's going to be quasi-isometric to the Euclidean plane, and it's sort of the ways of dealing with that, or it's quasi-isometric to the hyperbolic plane, and then we get this statement here, and then you have to show that this group that's quasi-isometric to the hyperbolic plane is actually coming from a proper isometric action on hyperbolic plane. You actually also care about other groups acting on S1 than just hyperbolic groups. There could be relatively hyperbolic groups happening there as well, and so on. Although that was already known due to Tukia. If there were parabolic elements, that was known previous to Casson-Jungras and Gabay. Okay, so good. Yep. Okay, so proof of convergence group theorem. And I'm not going to tell you Casson-Jungras' proof or Tukia's proof or Gabay's proof. This is after Markovich. Although I'm not going to give you the proofs that Markovich gives. He just reduces it to Tukia, and I want to sort of explain what Tukia does. And this is also related to things that were done by Nielsen and Zisheng. They had this idea, Tukia brought it into attacking the convergence group theorem. He reduced it to just what looked like just a few cases. In case the group has a rigid triangle group in it. And you're like, okay, well, that's a pretty special case. Let's just not worry about that. But that's the key case for proving this Seifert-Fibered conjecture, because that's the non-Harkin case of the Seifert-Fibered things, is when the quotient by Z is a rigid triangle group. Is sort of that's where all of the meat comes in. So that's really important. So Tukia didn't know how to deal with that case. He dealt with all of the other cases, and what he did was beautiful. Okay, so I want to give you this because I think it's really cool. And also you should think of this as a model for how Markovich proves his criterion in the two-sphere boundary case, but we're just going down one dimension, and it makes various things easier and easier to draw, but it's also easier. But this is pretty similar to what Markovich does. Okay, so here we go. Right, so we have G, so we have gamma, hyperbolic, boundary of gamma is S1. So let's just draw this here. There we go, circle. I'm looking to fill in the plane as the hyperbolic plane with an isometric action of gamma. Okay, so how am I going to do this? Well, so let's take some element gamma in gamma isomorphic to Z. Okay, so take an infinite order element. Every hyperbolic group has an infinite order element if it is infinite. Okay, that's a pretty straightforward thing. And so gamma acts on this circle with north-south dynamics. So there's a fixed point and another fixed point, gamma minus and gamma plus. And what does gamma do? It fixes these 2 points and it takes everything that isn't gamma minus and it stretches it towards gamma plus. Okay, you should think that there's an axis for gamma going through the middle of this disk and that we're translating the hyperbolic plane along this and the boundary gets sucked along in this direction as you do that. You should think that, except we don't have the hyperbolic plane. So we just see the action on the boundary. Okay. All right. These 2 points separate the circle into 2 components. After possibly passing to a power, they're fixed by gamma. Okay, so gamma is quasi-convex. Every Z subgroup of a hyperbolic group is quasi-convex. Okay, and well, up to passing to a power so that it doesn't swap these 2 sides, it's codimension 1. So this is a slight lie, but the thing generated by gamma squared is codimension 1. Okay. Great. So we have a cube complex.
What was the point of gamma squared?
So gamma might fix these 2 points and swap the 2 sides of the circle. Okay, so then there's only one orbit of component, and I can't apply this different orbits thing. Okay, and such endpoints, gamma plus or minus, for varying gamma, dense. They're actually dense in the circle squared minus the diagonal. So the pairs of distinct points on the boundary. Given any 2 distinct points on the circle and any open sets around those points, there exists gamma that is infinite order whose endpoints lie one in the one open set and one in the other open set. Okay, so this is what dense in the pairs minus the diagonal. Yeah, I do. Thanks. I said the right thing. Yeah, not definitely. I don't want to vary the group gamma. That's fixed. I want to show that there is a Fuchsian group. All right, so now we start again with this picture. You give me an A and a B, and they're different points on the circle. And now I can find gamma whose endpoints. So I find a little open set around A and a little open set around B that are disjoint from each other. So there's a point over here and a point over here. My open sets were intervals. I put a loxodromic, an infinite order element in there with its fixed points, and I cut it up. Okay. So I can apply Bergeron-Wise. So applies gamma is virtually compact special. Oh, sorry, Bergeron-Wise plus Agel. Bergeron-Wise implies it acts properly and co-compactly on a cat-zero cube complex, and Agel says that action is virtually compact special. I didn't know before right now gamma was even residually finite, but now I do, so that's great. So what else do I know now? What do I need out of all of these? Okay, so this implies that there exists a gamma naught and gamma finite index such that one gamma naught is torsion free. Okay, we haven't talked about why this is true. If a hyperbolic group is residually finite, it's virtually torsion free. Okay. That's because there's only finitely many conjugacy classes of finite subgroups. You only need to separate finitely many elements in a finite index normal subgroup. And so you can do that by intersecting them one for each finite order element that you need to make it normal. And then you've intersected then you've separated all of their conjugates as well. Okay, so that's something that's just true about residually finite hyperbolic groups. Sammy, are all hyperbolic groups residually finite?
Yeah.
Okay, great. I asked the right person.
Or actually, instances of groups, everybody can see the difference. in our-
Yeah, absolutely. Yeah, no. I also love the question, are all hyperbolic groups residually finite? And there, yeah, we can write down examples of groups where we don't know one way or the other. Yeah, absolutely. So work on that question instead. Yeah. For this group acting on the S1 boundary, I don't know why it's residually finite for a different reason. Do you?
No, but I thought maybe.
I mean, except that it follows from the convergence group theorem, which was proved in 1992.
Yeah, we just need that first. We don't need.
So I don't understand your question, Nick.
I'm sorry. We're using new stuff.
I'm trying to prove the convergence group theorem. Yeah. And just pretend you didn't read Gabai's proof or Casanin and Gross's proof when you were in grad school. Okay. I'm giving you a new proof that I hope you'll like better. But you probably won't. So actually Markovich just stops now. That wasn't a fire alarm, was it? Okay. I'll be on the lookout for it. Did it have its license plate? So if you read Markovich's paper, he says we give a new proof of the convergence group theorem, and he stops here. And why does he stop here? It's because Tukey already deals with, I've erased it, but it was here. Tukey already deals with the torsion-free case in 88, and that's much easier than the general case. But I think I'll explain sort of what Tukey's ideas are. And in order to do that, I want something a little bit better than that. So gamma zero has a quasi-convex hierarchy, and that's why I mentioned that consequence. And I want a third condition, and the third condition I will, okay, so for each of the Z subgroups that Bergeron Wise use to cubulate gamma, go again, to cubulate and the cubulate gamma. So the consequence of Bergeron-Wise theorem. Two more things are true. I should have used ABC so I could use I now, but anyway. So let's call such a thing gamma I. Gamma I intersect gamma zero is maximal cyclic in gamma zero. And B, let's call this this intersection gamma zero, gamma I hat. So it's generated by possibly some power of gamma I, is unlinked in gamma zero. Okay, what do I mean by that? Okay, so here I have my gamma I hat. My gamma I hat. I have a pair of points. When I hit it by an element of gamma zero, I'm going to get a different pair of points. I actually going to get two. Both points will be different. I can't just fix one of them and move the other one. So I'm going to hit it by an element of gamma zero. It's either going to fix these 2 points because it's a power of gamma I hat, or it's going to move these to 2 different points. Now, these 2 different points can do 2 different things. They can not link, or they can link. Okay, so I want all translates of gamma I hat under gamma zero to not link. Okay, so you should think of it as being like a simple closed curve. Okay, it's not immediately obvious why you can do this, but it's basically from the Q-surf properties of residually of virtually compact special groups. The things that the translates that did link before you pass to a finite index subgroup come from finitely many cosets, and separability allows you to get rid of those in a finite index subgroup. Okay. So exercise, if you want to come to the problem session and want something harder to do, like Dave asked for, prove that you can do this in this setting if you know something about cube complexes. All right, so we're in good shape. We have 10 minutes left, but that's okay. So I'm going to just draw a line topologically across this circle. And now I'm going to draw all of the orbits of this line. And if I do this with hyperbolic geodesics with some choice of metric, whatever, they're not going to link each other because of the non-linking condition. So I'm just going to pretend that these are hyperbolic geodesics. So I have this family of lines. This is sort of what Tukia does. Okay. I can extend the action from the action on the circle to the action on the circle union this family of lines. These lines are invariant under gamma 0. And I either act by translations on the line, and I just fill that in with a topological action by translations, or I move the lines around to different points in the lines. Okay, so I just do this for one of my families. This is gamma 1 hat. Okay, so let me write something. So draw some non-crossing lines inside S1 for each family gamma I hat translated by G in gamma 0. Okay, so the different families will cross each other for sure. Okay, but because you can see if I do this, there will be, yeah, anyway. Yeah. These 2 points are not separated by anything in my family, so I don't have enough with just one line, for example. Yeah, it means that you can do this. So if I take these 2 points, they link if they link. Okay, so if the 2 different points are in different components of the complement of the 2 points I started with. Okay, so it's a question of whether they're in different components or the same component when I hit them. Okay, and so unlinked means I can draw this picture, and linked means I would have to cross. Okay. So I get this family of lines, and they're all disjoint lines, and I claim I can extend the action of gamma 0 on S1 to an action on S1 union the lines for gamma 1 hat. Okay, just the first family. Okay, and what do I do when I get that? I get a bunch of disks in the complement of this collection of lines inside the topological disk. Okay, so the complement is now a collection of disks. Now this also corresponded to a hierarchy. The stabilizers of these regions are vertex groups in the first stage of the hierarchy. They're quasi-convex subgroups. And now they're acting on the disk. And their limit sets are going to be these Cantor sets that are coming in here. Okay, these disks are cut up by other families of lines coming from the other gamma i's that are like coming from, for example, gamma 2 hat. So now we cut these disks by the lines from gamma 2 hat. Okay, now you have to be a little bit careful to do that in an equivariant way, but it's possible. I don't know, maybe, yeah. But you can just, yeah. I mean, I think at this point it's pretty easy to finish. So I just wanted to sort of, yeah. Well, I'm going to do a different inductive thing. But yeah, so Mahan points out, and he's probably right. At this point, Stallings tells you that these vertex groups are free because, well, because I'm acting properly on a space with infinitely many ends. Now I might, yeah, and I made it torsion free, so I'm now free. And so you can probably finish from here if you want to, but maybe, yeah. Anyway, I actually think what I prefer to do is just keep cutting these disks up using the hierarchy that Haglund and Wise gave us. So I don't know. They do. All right, so I'm cutting up this disk, and now I'm just going to draw how the disk. Okay, I do exactly the same thing. I can extend to an action on this region union the lines that I got. And I can do this in an equivariant way because I drew the lines in advance. So I should have extended this in a way that respects the pattern of the lines. Exercise, you can do that. Okay, I keep going, and eventually I get regions that are stabilized by the groups at the bottom of this hierarchy, and those are trivial groups. So I inductively keep going. At the end, I get an action on a collection of lines whose complements are disks with trivial stabilizer. So that's once I've cut along all of the cyclic subgroups all at once. Just easy to extend it to an action on the disk. That's a free action on the disk. Okay, there's nothing left to do because there's no extra equivariance that you need to take care of. So now we can extend to a free gamma zero action on the disk. And that means that D2 mod gamma zero, on the closed disk, and D2 on the action of D2 of gamma on the open disk is a free action and co-compact. All of these regions are happening finitely. And so now D2 mod gamma zero is a surface. Okay, and then there's a little bit of mopping up at the end to make gamma zero actually Fuchsian, but one can do this. Because I'm done. I'm not done, but I'm done with this proof. There's just a massive clock here harassing me to stop very soon. But that's okay, because I only have 1 minute and 53 seconds of material left to say. You would have got a couple of minutes extra off, but now I'm not going to do that because Akasha.
I'll have to ask a question with you rather.
You can ask a question after I finish. How about that? Because we'll be time for questions. Okay. What I wanted to say is that if you want to do this in the two-sphere case, you do something similar. Actually, it's trickier. You take your thing, you cubulate it with surfaces. You pass to a finite index subgroup so that all of the limit sets of each one of these surfaces are a circle, and their translates are all disjoint circles. And now you extend the action on the two-sphere to the action on the two-sphere union a bunch of planes that you just artificially put in that are disjoint. Those planes are acted on by the surface groups. Great, we just use this theorem. And then you have an action on a ball and you extend that and you cut it up some more. And you eventually end up with an action on the ball compactified, where you had the original action on the two-sphere and the action on the interior chops things up into simply connected regions. And now you get a three-manifold. Markovich says, great, the gamma zero in this case is a Haken three-manifold. And so Thurston tells you that you are hyperbolic. And so that's Markovich's proof. Okay, so now I'll stop there and give you 38 seconds. Oh, you had a question first.
In that proof, which is a beautiful proof, what do you do with a triple of lines that pairwise intersect? Because there's two combinatorial configurations you can draw, basically like a right amongst your triangles, right? If you have two of them intersecting here, you could put the third one on one side or the other of the intersection.
Yeah, I draw all of my lines. Yeah, good question. I alighted that. Yeah, so see Tukia for more details. Yeah.
Or do you just put in a 3 cube and work with cube couples?
No. Tukia goes through the details of that, and I definitely lied about that bit, but that sort of argument is already in Tukia. Yeah.
If a hyperbolic group is a fundamental group of a special cube complex on the node, does the group admit malnormal quasi-convex hierarchy without any vertically additive?
Did you hear that question, Danny?
I was trying to hear.
Okay.
No, but I didn't hear it.
Yeah, so the question was, if you are a hyperbolic group that is the fundamental group of a special cube complex on the nose without virtual, do you admit a malnormal hierarchy on the nose?
You mean another hierarchy? The hierarchy that will come from the cube complex that you know about is not going to be. I think we'll talk about it afterwards. I think not. And then the possibility that there's some other crazy hierarchy that some other person made for you.
Who knows? Yes. Riley, did you have a question?
Oh, it got easier when we had like boundary, when we had these Keter set limit sets.
Yeah.
It get easier up one dimension if we have boundary.
Well, it should do. So Poincare duality implies that the half lives, half dies phenomenon from three-manifold topology still works. And I won't tell you what that is, but it was an exercise on the problem sheet. And so you should think of PD3 pair, the thing with boundary, as being Haken. Okay. What that gets you, I mean, something, but not very much. You should hopefully think it's easier to deal with that because Harkin 3 manifolds are easy to deal with than general non-Harkin 3 manifolds. But that's just a hope. That's not a mathematical statement at all. But you should hope that the case with boundary is easier. But let me point out, and I'll talk about this tomorrow, it is absolutely unknown whether a hyperbolic group whose boundary is a Sierpinski carpet is the fundamental group of a hyperbolic 3 manifold, or virtually. So that's also an open question. So prove that, and then that'll be a proof of concept that with boundary it's easier. Yeah, and we'll talk a bit more about this tomorrow. Is there another question?
Okay, so let's thank Daniel again